Hi, good day. So in our past discussions, we learned that the hydronium ion concentration or hydrogen ion concentration primarily dictates the acidity of a solution. That is, the higher the hydronium ion concentration or hydrogen ion concentration is, the more acidic the solution will be. Also, we learned that the hydroxide ion concentration primarily dictates the basicity or alkalinity of a solution. That is, the higher the hydroxide ion concentration is, the more basic the solution will be or the more alkaline the solution will be. And so, for example, if a person asked you, how acidic is this solution? And then, of course, you will reply, the acidity of this solution or the hydronium ion concentration of this solution is 7.2 times 10 raised to negative 3 molar. Now, this number here, 7.2 times 10 raised to negative 3 molar, might be a very vague number for a non-chemist person. It's like the same person will ask you how strong the earthquake is. And then, of course, you will reply, the strength of this earthquake is equivalent to 40,000 tons of trinitrotoluene or TNT that had exploded. Of course, that number, 40,000 tons of TNT or trinitrotoluene that had exploded, is a very vague number for that person. And so in earthquake, instead of using the equivalent tons of TNT or trinitrotoluene that had exploded, we actually use magnitude to describe the strength or power of the earthquake, right? Same with that, in chemistry, we should also use or we should devise another way or a way on how we can describe the acidity or basicity of a substance without using this vague number here, 7.2 times 10 raised to negative 3 molar, or the hydronium ion concentration, hydrogen ion concentration, or hydroxide ion concentration of a substance. And so in 1909, a Danish chemist named Søren Sørensen devised a way on how we can actually describe the acidity of a solution using this scale known as the pH scale. Okay? Now, the pH scale was first introduced by the Danish chemist Søren Sørensen in 1909. Okay? The exact meaning of P here is still disputed, but it is assumed to be potence. This one is potence, okay, which is actually the Danish word for power. Okay, so this pH here is actually assumed to be power of hydrogen or potence hydrogen. Okay, today P here in pH is actually read as the decimal cologarithm or the negative logarithm of. Okay, so negative logarithm of and decimal cologarithm of are just the same thing. Now, what's good about Sørensen's way in describing the acidity or basicity of a substance is that this P scale here, the P here, can also be used in any number or in other numbers or values. Okay, like for example, if we don't want to describe the hydronium ion concentration or hydrogen ion concentration, and we want to describe the magnesium ion concentration in a solution, then we can use PMG instead of pH. Or if, for example, we want to describe the boron ion concentration in a solution, then we can have Pb, power of boron. Okay, and so today we have now, aside from pH scale, we now have 4 major P scales that are actually used in chemistry. Okay. We have here the pH, pOH, pKa, and pKb. Power of hydronium ion or hydrogen, power of hydroxide ion, power of the dissociation constant for acid, and power of the dissociation constant for base. Now, earlier, we defined we said that today, P in pH is read as the decimal cologarithm of or negative logarithm of something that it actually describes. So for example, here in pH is actually read as negative logarithm of or decimal cologarithm of H or hydronium ion concentration. And so if we have here pH is actually equivalent to negative logarithm of hydronium ion concentration. This is now the mathematical formula for us to be able to find the pH of a solution. Okay, so negative logarithm of hydronium ion concentration or decimal cologarithm of hydronium ion concentration. Now, for example, in pOH, of course, that's pOH, power of hydroxide ion that's equivalent to negative logarithm of hydroxide ion concentration. So these p scales here are actually equivalent to decimal cologarithm of the thing that they are actually describing. If we have describing, like for example, if we have here PMG, we know that the formula for PMG, Mg is magnesium, PMG is equal to negative logarithm of magnesium ion concentration. If we have Pb here, B is boron, that's negative logarithm or decimal cologarithm of boron. So this p scale can actually be used in any elements that we have. Okay, so we also have here the pKa, the power of dissociation constant for acid, and that is actually equivalent to negative logarithm of the dissociation constant for acid, which is Ka, the thing that it actually describes. Okay, and we have here the pKb, the negative logarithm of Kb, or the dissociation constant for base. Now take note that pH and pOH are just actually reverse of each other, and pKa and pKb are actually reversed of each other. pH is a reversed pOH, and pKa is actually a reversed of pKb. Okay, and if we, for example, add the value of pH and pOH, it will always be equivalent to 14. That's why our pH scale here is up to 14. Okay, pH plus pOH is equal to 14. And so, for example, if someone asks you to find the pH of a substance, can you find its pOH? Yes, by using this formula. pH plus pOH is equal to 14. Also, pKa and pKb are actually related to each other. They are reversed of each other, and so similar to pH and pOH, pKa and pKb, if we, for example, add them, that is always equivalent to 14. So pKa plus pKb is equal to 14. So for example, if someone asked you to find the pKa of a substance, can you find its pKb? Yes, by using this formula. Okay, so we have here the pH scale. Okay, for the right part, we have here the pH scale. For the left part, we have here the pOH scale. Now, as we mentioned earlier, pH is actually a reversed pOH. Like for example here, one example of a substance that has actually a pH of 0 is 1 molar hydrochloric acid. Okay, and a substance that has a pH of 1, an example of that substance is stomach acid, and so on and so forth. As we have noticed here, water, okay, water has actually a pH of 7. It is actually in the middle of our pH scale. Okay, now if we are going to reverse this one, we are going to have here the pOH instead of pH. And so hydrochloric acid, which has actually a pH of 0, might have a pH of 14 in pOH scale. Okay, so ulit natin, hydrochloric acid that has a pH of 0 in pH scale might have a pOH of 14 in pOH scale. Okay, how about for example the vinegar? Okay, the vinegar has a pH of 3 but has a pOH of 11. Now, why are the pH, pOH, pKa, and pKb scales only up to 14? Now, that 14 here, okay, can actually be accounted for the water molecule. Okay, water is actually the basis of our pH and pOH scale. Okay. Now, this is actually the origin of 14 in pH scale. Remember that, according to Bronsted-Lowry acid-base definition, water can act both as an acid and as a base. Now, in a substance which is actually made of pure water, okay, water can actually react to itself because one water molecule can act as an acid and one water molecule can actually act as a base. So this water molecule here, which actually acts as an acid, will donate hydrogen to this water molecule which actually acts as a base. Now, after its donation to hydrogen, this water molecule will now turn into hydroxide ion, and this water molecule here will now turn into hydronium ion. Now, experimentally, it was determined that the hydroxide in this reaction, which is actually a reversible reaction, the hydroxide ion concentration of in water molecule in a pure water is always 1 times 10 raised to negative 7 molar. Okay, and experimentally, it was also determined that the hydronium ion concentration in a pure water molecule, in a pure water substance, is equivalent to 1 times 10 raised to negative 7 molar. Now, if we are going to use the p scale here, the definition of p scale here, or the p, which is the decimal cologarithm or the negative logarithm of, if we are going to get the negative logarithm of 1 times 10 raised to negative 7 molar, which is the negative logarithm of OH concentration, and the negative logarithm of 1 times 10 raised to negative 7 molar, the negative logarithm of hydronium ion concentration, then we could actually arrive here at 7. Okay, so here, we have here 7. Papakita ko sa inyo sa calculator. Okay. So, ito yung calculator natin. Okay, so negative log of 1 times 10, okay, times 10 raised to negative 7, parentheses. Okay, so the answer is, ayan, 7. Okay, so we have here 7, we have here 7. That's actually the OH concentration in water and the H positive or the hydronium ion concentration in water. Now, take note ha, H positive or H3O, parehas lang po yan. Okay? So, if you're going to add here 7 and 7, then we could have here 14. This is also the reason why, as we have noticed here in pH scale, okay, from 0 to 14, our water is actually at 7. And at pOH scale, from 0 to 14, still, the water is at 7. Nasa gitna siya. Okay? Because it's OH, pOH is 7. And it's H positive concentration or H2O positive concentration in pH, okay, is also 7. So, 7 plus 7 is equal to 14. Okay? So, that's actually the origin of 14 here. Now, take note that in p scale, again, we are using the decimal cologarithm or the negative logarithm of the substance or the thing that we are describing. Okay, and so because of this, because of the logarithm of a pH value, because of the logarithm of a pH value, a pH value is actually 10 times stronger than the value after it. Okay, so for example, we have here the stomach acid. The pH of stomach acid is 1. Okay, and we have here the lemon juice. The pH of lemon juice is 2. Okay, does that mean that stomach acid is just one step stronger than the lemon juice? No. Okay, that actually means stomach acid is 10 times stronger than the lemon juice. Okay, so another example. Okay, we have here the seawater and detergent. Let's compare them. Seawater, because we have here every step is actually 10 times stronger than the step that actually it preceded. So, seawater is 10 times stronger than the detergent. Okay, kasi isang step lang naman to, so times 10 lang. And lemon juice is 10,000 times stronger than the milk. We have here the lemon juice and the milk. Why 10,000? Remember this, one step is equivalent to 10 times. So, 2 and 3, that's 10 times. 3 and 4, that's another 10 times. 4 and 5, that's another 10 times. And 5 and 6, that's another 10 times. So, that's 10 times 10 times 10 times 10, or apat na 10, 10 times 10 times 10 times 10, or 10 raised to 4, which is actually equivalent to 10,000 times. Now, let's have an example problem where p scales are involved. Now, for this one, find the pH, pOH, pKa, and pKb of a substance with Ka is equal to 3 times 10 raised to negative 4 and hydronium ion concentration which is equal to 7.3 times 10 raised to negative 5. So for this one, we only have two given, the Ka and the hydronium ion concentration, but we are required to find the 4 p scales here, the pH, pOH, pKa, and pKb. Of course, the first values that we can actually get here are the pH and the pKa, because those two have actually the direct given. Okay, so for pH, we have the hydronium ion concentration given, and for pKa, we have the Ka given, or the dissociation constant for acid, that is actually given. Okay, so let's compute them. Again, pH is equivalent to negative logarithm of hydronium ion concentration. So we are going to use this formula to compute first the pH. So pH is equal to negative log of hydronium ion concentration. pH is equal to negative log of 7.3 times 10 raised to negative 5. So we are just going to substitute that here. And if we are going to do that in calculator, so negative log, okay, negative log for a while. Ayan, negative, saan yung negative? Negative log of 4.4, 4, mali pala. Negative log of 7.3 times 10, ito yung times 10, times 10. Sa iba, EXP yun instead of times 10, raised to negative 5. Okay, and we can have here 4.14. So our answer here is 4.14. So our pH is 4.14. How about for the pKa? pKa is equal to negative log of Ka. Okay, so again, magkaano lang sila ha? Parallel. pKa is equal to negative log of 3 times 10 raised to negative 4 because that is our given Ka here. So pKa is equal to 3.52. If we are going to do this in calculator, that's equivalent to 3.52. Now, can we compute the pOH directly from our computation, from our formula pOH is equal to negative log of OH negative? No, because there is no OH concentration that is actually given in our problem. So there is no OH given, so we cannot use this formula to find the pOH, but instead we can use this formula to find the pOH. So what we did was, since we already computed the pH, so pH is equal pH plus pOH is equal to 14. We know that the pH is 4.14, so we substituted this value to here. Okay, plus pOH, which is actually unknown, is equal to 14. By transposition, okay, to the other side of the equation, then we can have here pOH is equal to 14 minus 4.14, and therefore our pOH here is 9.86. Okay, how about for the pKb? Okay, for the pKb, we cannot use this formula directly, because we don't have Kb given here. But we can use this formula pKa plus pKb is equal to 14 to find the pKb. Okay, so what we did was we just substituted the value for pKa that we obtained a while ago. So pKb plus pKa is equal to 14, pKb plus 3.52. Okay, so we substituted this value here is equal to 14. pKb is equal to 14 minus 3.52. So we transpose 3.52 to the other side of the equation. So pKb is equal to 10.48. So that is how we can actually use the P scale in computing the pH, pOH, pKa, and pKb. So again, P scales are just negative logarithm or the decimal co-logarithm of anything that we describe. So for example, if we want to describe the power of lithium, PLI, that's actually negative logarithm or decimal co-logarithm of lithium ion concentration. If you want to describe the concentration or the power of beryllium, then that is negative logarithm of beryllium ion concentration, and so on and so forth. Okay, so that's all. Thank you for listening and good day.